Hello. So we are discussing two sample problems under module 3. Now this lecture is going to unfurl one more two sample location problem technique, which is called median test, and median test is quite common in the context of non-parametric tests for two medians. Okay, so not only the median test we are going to learn by this session, but we are going to learn mood test, which is another test for the scale problem, two sample scale problem. Okay, so let's start today's discussion. So all of us are well aware of the median. Median is the middlemost observation, so it's pretty clear to you. So there, suppose you have two samples and you would like to see whether the population from where these couple of samples come up, for those populations the medians are same or not. Okay, so that's the problem. Okay, so clear-cut case of a two sample location problem, because already I told you medians are treated as a location parameter in the context of the non-parametric statistics, right? So like Mann-Whitney U-test, two sample median test investigates if two independent samples are from identical distributions against the alternative that they have different location parameters. So here location parameters, we are taking the medians. Clear? The test may be used with data presented in at least an ordinal data. Okay, so these tests can be applicable for any kind of any type of data, but if you want to employ this median test in ordinal setup, then one set of observation must be ordinal. Okay, it can be usable while two set of observations are also ordinal, but one set must be ordinal. Okay, let there be two samples of sizes n10 and n20. So 1 means for first sample and the 2 means for the second sample, n10 and n20. From the true distribution under comparison, we ordered the total observations n is equal to capital N is equal to n10 plus n20. So you are combining these two samples. Clear? In a two samples format, which is in the combined structure. Next, we determine the combined sample median theta hat and we construct a two-way table thereby. So combined sample means you are merging all the observations, and after arranging the observations in increasing format, figure out which observation stands as a middlemost observation. Clear? So now we will have a two-way table. You can see a two-way table. Few observations from the sample 1 is less than the combined sample median theta hat, and few might be greater than theta hat. Remember, here we are not taking care of the case where observation exactly matches with the combined sample median. Okay, so equality case is omitted. Fine. In case of equality cases, generally in median test we drop it out, drop that observation. Clear? So sample 1 is n11, and sample 1, for sample 1 the observations are greater than theta hat is n12. Total observation, as we have seen, n10. And for sample 2, the observations which are less than the combined sample median is n21 as well as n22 can be figured out. Now you will see that n11 plus n12 is n10. So that is called the marginal. Okay, n10. Similarly, n21 plus n22, that is n20. So this is the marginal. And similarly, you can figure out N01 and N02. So don't get confused by the notational jargons. I would rather say that N10, N20. You have to remember that is on the basis of the combined sample median, you are making a segregation in sample 1 and in sample 2. Obviously, the total observations, when you are adding N10 and N20, you will have capital N. If N10 and N20 are small, exact probability of the above table can be found using hypergeometric distribution, which is just, you can see, N10 factorial, N20 factorial, N01 factorial, N02 factorial divided by, these are the all cell frequencies. Within the cell, you will have N11, N12 factorial, N21 factorial, N22 factorial, and the entire stuff will be divided by N factorial. So N factorial, N is the total observations present in the combined sample. Now, where factorial, all of you might not have the idea regarding the factorial. So factorial operator works like, if we consider a factorial, that is nothing but 1 to 2 to 3. That means you have to multiply till a, multiply all the natural integer till a. Clear? So for large N10 and N20, each greater than 10, we can use an approximate test statistic, and which is chi-square, and the format of the chi-square is this: N11 N22 minus N12 N21 whole square divided by all the marginals. Look at the denominator. Denominator comprises the product of all the marginals. So this expression follows a chi-square distribution with degrees of freedom 1. So this test may be used with data presented in at least an ordinal scale, already I have told. Now, once you know this chi-square, once you know this probability, then the rest is just the calculation left, right? Let us have one quick example and try to solve this example manually. The following are the marks secured by 2 batches of salesmen in the final test taken after completion of training, and check if the medians of 2 batches are the same. So that is my concern, right? So what is your null hypothesis? The basic question: the population median of batch A is same as the population median of batch B. Right? This is your null hypothesis. And what would be the alternative hypothesis? I haven't written the alternative hypothesis here, but the alternative hypothesis will be just not equal to. Clear? So this is batch A and batch B. The first thing is, you have to arrange the observations in increasing order and in a combined format sample. So you will figure out what is the smallest one. 19 is the smallest one, which occurs in batch A. What is the smallest one in batch B? That is also 19. That means 19 occurs twice in the combined sample. But the beauty of median test is, it doesn't get bothered about the repetitive observations, about the tie case of the observations. Unlike the previous Mann-Whitney, unlike the previously discussed Wilcoxon Mann-Whitney test, right? Okay, so now we will have to figure out, so this is the arranged observation. How many observations are there? First sample observation 9, second sample observation 6, altogether 15th observation, and sample median will be located as the 8th observation, because 15 plus 1 divided by 2, that is 16, that is 8th observation. And which observation stands at the 8th position? Let us count from the left hand side. 1, 2, 3, 4, 5, 6, 7, 8. So 25 is the median of that combined sample. Now on the basis of this 25, let us write the two-way table. How many observations from the first sample is less than 25? How many observations from the second sample are less than 25? Similarly, how many are bigger than 25? So bigger than 25. Is there 25? Yes, 25 is there. But here I haven't dropped that exact 25 observation. It depends on you. Although I have told you that for bigger set, you can drop that median value 25. But since these example comprises of small values, both of the values are less than 10. Remember, less than 10. One is 9, that is also less than 10. Another is 6, that is also less than 10. So it's better not to lose any information by dropping that equal observations, right? So that's why I haven't dropped that out. So this is the two-way table. 25, how many observations from the first sample less than 25 is very easy. Just count it out. How many observations are there? 21, 20 and 19. So 3. So rest is 6. So this is the entire stuff, 3 and 6, 4 and 2. And similarly, you can figure out the marginals. Add 3 plus 6 is 9. Add 4 plus 2 is 6. Quite obvious because the first sample comprises 9 observations while the second one is holding 6 observations. So that's what is happening here. And 4 plus 3 is 7. That in the combined sample, 7 observations are less than 25 and 8 observations are greater than equal to 25. Now the probability, because less than 10, the marginals are less than 10, we will stick to the exact probability calculation. And in exact probability calculation, you know the formula. The rest is extremely easier. Replace the values and the factorial. Say if I am calculating out 9 factorial, then I have to multiply 1 into. So let me write it for your convenience. So when 9 factorial means 1 into 2 into 3 into then 8 into 9. Similarly, figure out what 6 factorial is, figure out what 7 factorial, figure out what 8 factorial will be. Now you will see that most of the time the numerator observations get cancelled out with the denominator because 6 factorial happens both in numerator as well as both in denominator. 7 factorial and 4 factorial is till 4, 7 factorial is till 7. So obviously that 4 factorial part will be embedded in 7 factorial. What will be left over? 6, 5, 6 and 7. So the computational labor is not that much strong. Okay. So P comes out as, probability comes out as 0.1958. And if you fix your alpha is equal to 0.05, even though I am writing here alpha as 0.05, mostly while dealing with this type of small data, alpha is taken in practice as 0.1, a little higher. Okay, the rejection probability of type 1 error is set at a little higher place, 0.1. So you can do the same problem with 0.1. So what we can see that these calculated probability is less than, it is greater than alpha, and if it is less than alpha then we'll have to reject, but here in this case it is greater than alpha, so we failed to reject the null hypothesis. So what was null hypothesis? Just a quick return to the null hypothesis. It says that population median of batch A and batch B of population median of batch B, they are equal, they are the same. So you can conclude that the medians of the two batches are same, right? Now you can use the same problem by R. So let me open R window. Okay, in R window, to have the median test, first you have to install the package agricolae. Okay, so AGRICOLAE. Now you remember how do you install a new package? You can go to the package, you can have that install option here, and you can, once you are ticking it down, you will have that CRAN repository, that is an online cloud online repository where all of the R packages are stored. So in case your own system doesn't have that package agricolae, then you can just go to the CRAN repository and type the package name here, agricolae, and you will make it downloaded to your system. But in my system, I have already downloaded this specific package. So what we will write? Library. That means I need to recall that package from my own built-in library. Library, quote unquote, agricolae. So run it down. Now one more thing while going for median test. See, in median test you are dealing with two types of batches, two types of treatment. In R language they are called the treatment. So you have to first make the treatment wise segment. Clear? Treatment wise segment. So the first observation is treated or assigned by 1, and the second observation is assigned by 2. So there are two groups, remember that. First group is 1, second group is 2. Now under this group, how many observations are there? In the first group there are 9 observations. So 1, 9. You see repetition. So 1 will be repeated, first group will be repeated for 9 observation, 1, 1, 1, 1, like that till 1, altogether 9 batches. And second group will be repeated for 6 observation, right? So 2, 2, 2. Okay, let me run it out and you will understand what I am trying to mean. See how the observations are assigned by the number of the group. There are 2 groups. In case you have 3 groups, then again you have to write, suppose you have another group, third group having 4 observation, then you will have to write 3 and 4. But for this problem we have only 2 groups. So if you run it then and write TRT, you will see 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 3, 3, 3, 3, 3. Okay, let me erase this out. Okay, now it's time to write all of the observation in any sequence they appear. No need of arranging them. You can just write all the observation manually. So did I. So this is the combined sample format. 26, 27, 31, 26, 19, 21, all the observations. So altogether how many observations? 9 plus 6, 15 observations. And the rest is extremely easy. You have to write median. Remember, M is capital, median dot test, which is a function already inbuilt in this library, agricolae, and Y. Y is your data set. Never forget to append this TRT, comma TRT. That means you are trying to make the median test over this structure of grouping, over this structure of treatmenting. So run it out and you will have this thing, this output. Okay, let me get you down to this output, how to read that output. Now first you will see that R cannot give you the exact probability. Remember out, even though 9 is less than 10, 6 is less than 10, exact probability is not possible in median.test function. What R will do? R will give you that approximate chi-square test, and that's what is there. Chi-square value is 0.7142857, and the degrees of freedom, as you know, is 1. And look at the p-value is 0.3980, which is quite high, I would rather say. And median is 25. What does it mean? Median is 25 means the median of the combined sample. Already we people have seen it, that combined sample median is 25. Not only that, it will give you the class-wise, the group-wise 5-point summary. This is called 5-point summary. Median, number of observation, minimum observation, maximum observation, first quartile and the third quartile, so that you can have a check regarding the distribution of two different groups. Clear? So you can figure it out individually as well. The most interesting part, which I would like to draw your attention down, that is the post hoc analysis. What does it mean by post hoc analysis? Post hoc analysis identifies which specific group pair is different. In our case, in this particular problem, there are only 2 groups. So post hoc analysis is easier, but in case you have 3 groups and you would like to check whether the median of each of the groups are same or not, okay? So mu1 median is equal to mu2 median is equal to mu3 median, then post hoc analysis will be of your great help. So in this case, you will look at this. The treatments with the same letter are not significantly different. That's how you have to read the post hoc analysis. So in this group, you see A and A, that means first group as well as first group. First group is 26 median. You can always make a verification from that median 5-point stuff. Second group is 23.5 median, even though we are writing A and A. That means although we are having 2 separate groups, but basically they are coming from the same population, and that's why the population is denoted as A and A. That means it is referring back to the same population. So when you are doing the same stuff with 3 groups, that is, as I am saying, 3 groups, then you will have post hoc analysis give you 3 parts: A 1-2 group, then 1-3 group, then 2-3 group. And just by looking at the picture, looking at AA, or it is AB or BC, you can understand that which pairs, which medians are not equal. Okay, so when we are comparing, always we'll have to make pairwise comparison, right? So AA means there is no difference between the 2 population in terms of median. So in case it is AB, then that means 2 population medians are different. So it's very interesting. I am putting on one question or one query to you, that take a 3 group sample and make a median test to check whether all 3 populations from where these 3 samples have come, the medians are same or not. Okay, let's get back to the PPT presentations again. So far, whatever we have discussed the 2 sample problem related to the location. So we have done Mann-Whitney test, we have done Wilcoxon Mann-Whitney test, as well as we have discussed median test. Now the next concern will be two sample scale test. That means two distributions are there. Suppose these two distributions are having the same location parameter, right? But they are different as per their scale parameter. What is a scale parameter? You people know the scale parameter means measure of dispersion. That means they are different in terms of, say, variance, in terms of, say, quartile deviation. So all of the measures of dispersions are concerned here. But since we are talking about non-parametric, we cannot say that they are different only by the variances. In parametric test, what you have done sigma 1 square is equal to sigma 2 square, null hypothesis is. But that is the parametric setup. Here we will see that, well, let us take theta, which is just a scale parameter, and we will see whether x, the scale parameter of x observations are same as the scale parameter of the y observation. More general tone. Okay. So what is two sample scale problem? Remember the scale model, when two populations are different by scale parameter, once their location parameters are equal. That's very essential point. That is, subject to the condition their location parameters are same, you are checking whether the two populations are different by their scale parameter. By non-parametric dispersion, we mean scale means the spread, the scatteredness around the respective medians. Since x and y populations differ only in scale, the alternative hypothesis is H1 Fyx is equal to Fx theta x. So theta is the scale parameter, and scale parameter must be greater than 0. It is always positive, and theta is not taken as 1. Why? If you take theta as 1, what did you find? If we just replace theta as 1 in alternative hypothesis, then Fyx will be Fxx. That means two distributions are same. So theta is equal to 1 is the concern under the null hypothesis. Clear? So the cumulative distribution function of y population is the same as that of the x population, but with a tone of compressed or enlarged scale according as theta greater than 1 or theta less than 1. Compressed means more coagulated, more squeezed, and enlarged means more scattered. Okay. So the null hypothesis, theta is equal to 1, that is my null hypothesis, against the alternative hypothesis, theta not equal to 1. Of course, if you are trying to be more specific, you can make the alternative hypothesis one-sided, theta greater than 1. So in case you are taking Fyx is equal to Fx theta x, y is more compressed, more squeezed if theta greater than 1 here, and y is enlarged as compared with x if theta less than 1. Now how does it happen? Just think from your concept. So look at these diagrams below, clear will be your idea. Suppose two distributions have the same location. Okay. So Fyx and Fxx. So look at the first one. These two are the distribution function. So along x-axis, all of the observational values are going to be jotted down, and along y-axis, the distributional functions are drawn, one in purple color, another in green color. Now I am claiming that y is more compressed. More compressed means less dispersed or less scattered, right? If theta is equal to 1, let's take theta is equal to 2, theta greater than 1. This is my alternative hypothesis, theta greater than 1. Okay, let's take a specific value of theta. Theta is equal to 2, x is equal to 4. a particular point-wise clarification we are trying to build. Fyx is equal to Fy4. Fyx, small x, is the value taken by both the random variable capital Y and capital X. Clear? So, probability capital Y less than equal to 4. Now, capital Y less than equal to 4 is x less than equal to 2 cross 4, right? Because what is my alternative hypothesis? Fy small x is equal to Fx theta x. So, when I am writing small x is 4. In terms of capital X, in terms of the random variable capital X, we have to write 2 into small x. 2 is the value of the theta. Okay. So, writing y less than equal to 4 is same as writing x less than equal to 2 cross 4. Clear? Now, take a look. X by 2, I am just taking 2 on the left hand side, x divided by 2 less than equal to 4. Now, have a check. Fy4, y less than equal to 4 means writing x by 2 less than equal to 4. That means y is more compressed, isn't it? Similarly, take theta is equal to half. Have a check over this picture, that is Fxx, and the lower curve is Fyx. Y is more enlarged. More enlarged means Fy4, which is y less than equal to 4. This probability is same as the probability taken by twice x. Clear? Once you are fixing 4, then the probability taken by y till the point 4 is same as the probability amount taken by twice x till that point 4. That means x has to go larger to that point as y already reached. So, y is more enlarged. So, this is the concept of compressed distribution and enlarged distribution, and on this basis your scale parameter has to be checked, has to be tested. One particular non-parametric scale test, which is also a non-parametric analog of that F-test under parametric setup, where you have tested H naught is equal to sigma 1 square is equal to sigma 2 square. Clear? That is mood test. It is widely used non-parametric scale test, two sample non-parametric scale test. Let x1, x2, xn1 and y1, y2, yn2 be two samples of independent observations drawn from two population fx and fy respectively, not from the normal. Okay, so they are just two continuous population. Better to write continuous population. Okay, I have missed it. You people please make it a note. They should be continuous. First, we rank the n is equal to small n1, n2 observations from the two samples and denote Ri, the rank of x observations in the combined ranking. You can take Ri as a y observation, but you have to stick to one sample, and that's what I did. I have taken x observation is my point of concern. So, Ri being the rank of x observation. Mood test is based on the sum of the squares of the deviations of the x ranks from the average combined rank n plus 1 by 2. What will be the combined rank? That will be 1 to capital N, right? So, what will be the sum of all ranks in the combined sample? 1 plus 2 plus 3 plus till plus n. So, average combined rank will be n into n plus 1 divided by 2 and divided by capital N. So, n cancelled out and you will have average combined rank as a result, n plus 1 divided by 2. The test statistic, the mood test statistic Mn is equal to Ri minus n plus 1 by 2 whole square. A large value of Mn implies X's are more dispersed. That is extremely essential to understand. So a large value of Mn, that means X observations are taking the higher side of the combined sample. Obviously, that higher side means the ranks will be towards the higher side. Ranks of the X observation, I mean, towards the higher side. Clear? So X are more dispersed, that means theta greater than 1. Y, X are more dispersed means, on the contrary, Y's are more compressed. And a small Mn implies Y's are more dispersed. So that's how you have to build the alternative hypothesis. For two-sided alternative, we reject null hypothesis if Mn is too small or too large. Remember, theta greater than 1 or theta less than 1 depends on how the null hypothesis is set. The exact null distribution of Mn can be derived in small samples by enumeration. However, for large N1 and N2, normal approximation may be used to get the critical values. For computational complexity, we are not going to solve the problem manually, rather we will use R command. Now let's have a quick example, and later on we will switch to the R console, R window. First, let us go through this example. Suppose in a college you conducted a survey among students to find out how many cups of coffee or tea they drink per week. You have chosen students from maths major and that from psychology major. Below is the data based on 7 students from maths and 8 students from psychology. Do you believe that these two distributions between maths and psychology students differ by the scale? That is the key point, differ by the scale. Clear? So these are the number of cups of tea or coffee usually the students take in a day. So 23, 10, that means the first student from maths major, he or she takes 23 cups of coffee, quite bad, or cups of tea in a day. Then 10, then 17, then 11, so on and so forth. I hope that problem is clear. The median of maths is 12 and the median of psychology is 9.5. It's pretty easy. You can figure it out. The assumptions you have to take before jumping into the mood test, or jumping into the test of scale, is the underlying population have equal location parameters, but they are different by the scale parameter. So it is a two-sided test because different can be both greater than side as well as less than side. So not equal to. Now let's get to the R window. Okay. Example 1, 23, 10, 17, 11, 12, 13 and 4. So maths students records are like that. Psychology students records are like that. Let me run this. You can figure out the median. I have already mentioned you the median of the math student, but if you go for 5 number summary, 5 num, that is the syntax you have to use. You can see that minimum is 4. Look at the console. Minimum is 4. Then first quartile is 10.5. Median, look at median, that is 12. And third quartile is 15th, maximum is 23, so on and so forth. Median, just for your concept building, just for your interest, you can just check that how the medians are there. Median for the psychology student is this. Although we have said that the median, the population medians for both maths and psychology, they are same. We have assumed that. But here we can see for math student the median is 12 and for psychology major student the median is 9.5. There is a little difference. You can make a box plot as well just to have a visual impact how the distribution for these two classes differ. But let me get straight down to mood test. Mood.test. Mood.test is a inbuilt R syntax already in stats mass. So no new package you need to install. Okay. So maths and psychology, Z is 0.37235. This is the standardized mood value. Okay, whatever I have shown you, that is the mood test statistic, but if you standardize it, you will have 0.3723. And look at the p-value. P-value is 0.70, which is quite high. So you can conclude that the null hypothesis is accepted, or we fail to reject the null hypothesis. Let's get back to one more problem in PPT. Example 2. Psychology departments of public universities in each of 2 different states accepted 7 and 9 applicants. You can see University X and University Y. The sample median and mean score of the applicants of the 2 universities are close to being equal. So an assumption of equal location may well be justified. Report the p-value. Okay, so we will go to the mood test first. And for mood test, once again, we have to go back to the R console. See, in the R console, example 2, you can see University X, University Y. Now question is, are both of the population really a symmetric distribution? You can draw the box plot. You will see that there are 2 university box plots are there. And are they following normal distribution? Because always I told you that you will go to the non-parametric methodology once you are sure that the observations are not coming from the normal distribution, right? So you know the technique I already mentioned. Why not draw QQ norm of University X? QQ line, it will show the difference from the theoretical quantiles, and the dots are the simulated or sample centric quantiles. You will see almost all of the points fall on this. So one can assume that first university is from the normal distribution. But well, for the sake of our learning session, let us assume that both of them are from non-normal distribution. Okay, so let's get down for the mood test. And what is the value for mood test? See, mood test, the minus 2.4017. You can ask me that why this is minus, because I told you that is the standardized value. Minus 2 is the standardized value. Value minus expectation divided by the variance, and p-value is 0.016, which is smaller than 0.05. So mood test say that University X is different to University Y as far as the scale is concerned. There is one more alternative to mood test, that is also I am going to show you, that is called Ansari test. And Ansari test is also available in the stats package in RStudio, and that is ansari.test, the same thing. You see, ansari.test, and what is the output for Ansari test? It is completely different, AB, but look at the p-value. P-value is 0.029. P-value is 0.029. So this p-value is also less than 0.05. You can have the idea of rejecting the null hypothesis. Okay, let me get back to the PPT again. As I was saying that there is one more alternative to mood test, because that alternative is required, it holds better power But we are not going to that much deeper of non-parametric statistics. So let me give you just the flavor of Ansari-Bradley test, and we have already seen it in our code that the same problem can be tackled either by the mood test or by the Ansari-Bradley test. So it is a refinement. In Ansari-Bradley test, the absolute value of the deviation of each rank from its average rank is summed up, but the absolute deviation is considered. So summation modulus of Ri minus n plus 1 by 2, where Ri is the rank of X observation. There are several variations of these statistics in the literature, but they are all equivalent. R uses, mark my word, R uses this modification of Ansari test, and it is generally denoted by capital Fn, N1 into capital N plus 1 by 2 minus An. What is N1? N1 is the X sample observations, okay, and capital N is the total number of observations. Ansari-Bradley test criteria is just the reverse of the mood test criteria. Reverse of the mood test criteria, that is, a small value of Fn suggests that the X has larger dispersion. But we are not bothered about this, because while we are passing through R, we always look at the p-value, and we know for p-value the rejection rule remains the same. When you are dealing with the critical value, then you have to be very cautious while making the rejection, whether it is left-sided or right-sided, whether the test statistic is bigger means the rejection will be stronger, probability of rejection will be stronger. But these type of hazards are not encountered when you are dealing with p-value. P-value greater than 0.05 means you accept the null hypothesis, and less than 0.05 means you reject the null hypothesis. So in Ansari-Bradley test, I have already made the screenshot of the R thing. In the first problem means the maths major and psychology major problem. We have done the Ansari test for the second problem, but the maths major, psychology major, you will have AB, that is the test statistic value 30.5 and p-value is 0.8826. And see this warning message, it comes as there are ties in the combined sample. So when there are ties, as we are assuming the continuous pattern of the distribution, so two observations cannot be same. But in practice, in real life, we know that sometimes you have to encounter the tie case. So warning message is for the tie case. In first problem, there are few repetitive observations. So what will be the way out? As I already taught you, whenever you have tie case in your data, just incorporate this: exact is equal to false. That means we are not in need of exact probability distribution of the test statistic. Exact is equal to false. Clear? So in mood test, this warning you will not find. That is another merit of mood test. Okay. So here also you will see, as p-value greater than 0.05, H0 is accepted. So you can make a practice on your own and you will have the idea. There are few highlights I would like to mention, because sometimes we get confused whether mood test, whether Ansari-Bradley test, which one we will choose, which one we will pick up. Mood test or Ansari-Bradley test is the non-parametric analog of F-test on equality of variances when two underlying populations are assumed as normal. Okay. In fact, Fisher's t-test, parametric test on equality of two means under two independent normal population, is based on the assumption of equality of two population variances. This assumption can be checked through F-test when underlying populations are normal. F-test means you have to see that whether these population variants are same. So under normality assumption, you can make a check through F test. But if your populations are not normal or skewed, in that case, mood test can be used for checking the equality of two population variances. In this regard, Levin's test, a test is very popular, Levin's test, to assess the homogeneity of variances for two or more classes for two groups may be substituted by mood test when underlying populations are non-normal. So in case someone asks you that what is the non-parametric analog of Levin's test, that is mood test, that is Bradley-Ansari test. Under the assumption of normal populations differing only in variance, the asymptotic relative efficiency of the mood test relative to F test is 0.76, while the asymptotic relative efficiency for Bradley-Ansari test to F test is 0.608. But remember, that is when you know the distributions are normal. Then the efficiency, relative efficiency of mood test is 0.76, it is bigger, and Bradley-Ansari test is 0.608. But in case your distribution populations are not normal, then Bradley-Ansari test will be more efficient. Okay. So that's the part. Already I have discussed the example too, but in this part, I am just trying to show you the p-value, how p-value differs for F test, which is under the normal assumption 0.0319, mood test 0.0163, and Ansari-Bradley test 0.0297. Same problem, but three different p-values. Now, you can understand that which one is more restrictive. Lower the p-value, more restrictions are there. So mood test is more restrictive. You can see 0.016 is the lowermost value. So that's all about the two sample non-parametric scale test, and we will learn when and why we would use the mood test or Bradley-Ansari test. But of course, before that, you people have to check the structure, the distribution of the sample at your hand. Look at the box plot, make a test, F test, general F test, look at the QQ norm, quantile plot of normal. And if you are sure that no, the distributions are not normal distribution, then you can always have a choice to opt for non-parametric statistics. Thank you.